the concept of magnetic flux. Dorstetter, what is the symbol for flux?
Oh, it's capital P.
It is a capital Phi. What does a capital Phi look like, Winter? Ah, close. It's usually like that with a 2. Sometimes you do see it without the 2 other lines as well. Usually I think that's a lowercase phi. You see that? And it is going to be magnetic flux as opposed to electric flux. So it has a subscript of a capital B. And it is equal to, just like electric flux was equal to E dot dA, magnetic flux is equal to the integral of B dot dA, magnetic flux. So you've worked with electric flux before. Magnetic flux is just substituting magnetic instead of for electric field. So it would be equal to BA times the cosine of theta if you have a constant magnetic field, area, and theta. And it is literally the number of magnetic field lines through a plane. And I don't need to get into the fact that magnetic field lines are something that we made up to represent the direction of the magnetic field and all that stuff. It's still just an imaginary thing, but it's good for the purposes of understanding what's going on. So let's just look at, for example, if we have a magnetic field that is going this way. We could have a current carrying loop that is oriented like this. If the current carrying loop is organized like this, with the current out of the board here and into the board on this side, in other words, the current is going this way, that would give an area vector. If you use the right-hand rule, the area vector would be up, and therefore the angle between the magnetic field and the area vector would be 90 degrees. Cosine of 90 class is 0. So the magnetic flux in this particular case would be equal to 0. Because if you look at it, the number of field lines passing through this particular loop would be equal to 0. We can do the same thing if we were to just instead look at it as this and turn our wire, our loop, so that it's like this with the current coming out of and into here. Again, we're going to end up with an area vector which is going to be this way. Here we're going to have a theta of 0 degrees, and our magnetic flux in this particular case is a maximum. It would have the maximum number of field lines going through it if the area vector is in the same direction as the magnetic field. The dimensions on magnetic flux, please. Mohit. Walk through it. So you've got BA cosine theta. What are the dimensions on the magnetic field?
I'm trying to remember.
Ah, sorry. I was trying to help. Gary, dimension of the magnetic field.
I do not remember.
Oh. Miller.
Tesla's?
Tesla's.
Fudge.
Times Mohit.
Meters squared.
Meters squared. And cosine of theta is not going to give you anything. So it is Tesla's times meters squared. These have their own name. It is called a Weber. WB for Weber. Now, actually let's do this first. There is going to be a whole lot more on magnetic flux in chapters 31 and 32. We get to deal with the derivative of the magnetic flux as a function of time. It's quite fun. We're not there yet. At this point in chapter 30, we just basically learned this and one little other piece, which is Gauss's law in magnetism. Gauss's law in magnetism. A closed loop integral of B dot dA is equal to this comes from what we know about magnetic field lines. Magnetic field lines always come in, who can answer that? Who can finish that? Magnetic field lines always come in pairs. No, the magnetic poles come in pairs. I agree with that. It's because, as far as we know, we've never found a magnetic monopole. Because magnetic poles always come in pairs, magnetic field lines are always loops. They are always closed loops. Because magnetic field lines are always closed loops, what is B dot dA equal to, the closed loop integral of B dot dA? The number of field lines going into, or the number of magnetic field lines going into or out of the loop. The Amperian loop, or Gaussian surface. Gaussian surface. 0. You're going to have the same number going in as you are going out. If we look at it, we start with today's desktop picture. Today's desktop picture is from a University of Michigan women's basketball game. We made a sign, you feel the enthusiasm. Let's see. Here is a visual. The loops, the magnetic fields are always in loops. So if we draw an Amperian surface, I'm sorry, a Gaussian surface, if we draw a Gaussian surface, every magnetic field line that goes in will also go out of that surface. Hence, the magnetic flux for a closed surface will always add up to